A soft morning light seeps through the curtains. You awaken with a quiet inhale. The world is still. You remember the night before, that close call, the car that swerved, the moment your life hung in a delicate balance. Your heart was pounding, yet here you are, alive and blinking in the dawn. It feels like a second chance. You sit up slowly, the sheets rustling. You recall the wave of relief, the thought, that was a near miss. I could be dead. A shiver trickles down your spine. Why are you here, now, noticing that you survived? Why this outcome, when it so easily could have been otherwise? Outside, a bird chirps. The world looks ordinary, but a gentle, unsettling question has taken root in your mind. One you can't unask. What if the reason you're here to notice the near miss is that you can only ever notice the timelines where you survive? In all the branching roads reality might have taken last night, you wake up only in the ones where you're still alive. No claims, no certainties, just a whisper of a possibility. A what if that lingers like the hush after a storm. If reality truly branches into many possibilities, why do you always find yourself in the branch where you're still here? Let's gently step back and set the stage. To understand this eerie question, we need a bit of quantum foundation, but don't worry, we'll keep it calm and clear. Quantum mechanics is famously strange, but it's not magic or mysticism. It's the rigorous science of how the universe behaves at its smallest scales, and sometimes reality simply refuses to behave like our everyday classical intuitions. At the heart of quantum theory is a thing called the wave function, a mathematical object that describes a system's state as a blend or superposition of possibilities. An electron isn't here or there. In the math, it can be in a combination of here and there, multiple states at once. This isn't an issue while it remains unobserved. The weirdness comes when we measure it. Upon measurement, we observe a definite outcome. The electron is here, say. The long-standing puzzle is why we see just one outcome when the theory's equations allowed many. This is known as the measurement problem, the pain point where quantum reality and our observation of reality seem to clash. Different interpretations of quantum mechanics step in here, and it's crucial to clarify. Interpretations aren't different equations or different experimental results. They're different stories we tell about what the equations mean. By design, all mainstream interpretations make the same predictions for any lab test. If they didn't, they wouldn't just be interpretations, they'd be different theories altogether. So, choosing an interpretation is about how you conceptualize what's going on behind the scenes, not about changing the successful math. Why have interpretations at all? Because quantum mechanics delivers astounding accuracy, yet offers no intuitive picture of reality in the way classical physics did. It's as if we have a perfectly working machine, but no agreement on what the machine really is. Some physicists are content with just the machine. Others want to know what's actually happening, hence a slew of interpretations, each trying to answer the riddle of Schrödinger's famous cat, the cat that, according to the equations, could end up alive and dead until observed. One interpretation, the one we're exploring here, is often called many worlds. It emerged as a bold proposal to resolve the measurement problem without adding anything mystical or ad hoc. In the 1950s, a graduate student named Hugh Everett III dared to ask, what if the wave function never collapses at all? What if every possible outcome described by the equations is real, just realized in its own branch of the universe? Everett's idea was that the quantum equations, like Schrödinger's equation, apply universally, with no special case for measuring devices or conscious observers. The universe, including any observers, always evolves according to the same quantum rules, which are linear and unitary in physics jargon. Under these rules, a measurement doesn't destroy possibilities, it spreads them out. The classic example, Schrödinger's cat, before you check, is described by a superposition, a kind of both and, of cat alive and cat dead. When you open the box, standard law says the superposition collapses to one reality. But Everett said, no collapse. Instead, the act of looking entangles you with the cat's state. The universe's wave function includes you seeing a live cat and you seeing a dead cat, two outcomes that both exist, but in different branches of reality. Each branch is a fully real world, with a you, a cat, and a consistent history. You experience just one outcome because you are now part of that branch, unaware of the other branch where another you saw something different. In this many worlds view, what we call a measurement is just a process where quantum possibilities split or branch into multiple, non-communicating realities. The universe becomes a constantly branching tree of outcomes. It's important to note, these branches are not creating new universes out of nothing at the moment of decision. They were already implicit in the one-wave function of the universe. They were always possibilities, and the act of measurement just lets them decohere into separate, non-interfering realities. The total reality, the multiverse in this context, still obeys the same deterministic wave function evolution. It's just that from any given branch's point of view, it looks like a random outcome happened, and other possibilities vanished. In truth, nothing vanished. Those other outcomes just happened elsewhere. If this sounds mind-bending, you're not alone. Even Erwin Schrödinger himself, who formulated the famous cat paradox, had mused about these multiple outcomes. In 1952, Schrödinger wrote that it seems lunatic, but possible, that all outcomes really happen simultaneously. He jokes that physicists feared reality would turn to a quagmire or jelly if all possibilities were real. It feels crazy because our common sense insists there's one world, one outcome. Everett's move was to accept the math at face value and say, the outcomes all exist, just in branching worlds. This way, he removed the mysterious wave function collapse that Copenhagen interpretation had added as a kind of band-aid to force one outcome. Everett wanted a universe with no band-aids, just pure quantum evolution everywhere, all the time. Before we move on, let's ground this with what many worlds really implies. It asserts that the universal wave function is real as an ocean, and it never collapses. All possible outcomes are like ripples that keep flowing. When a quantum event with multiple outcomes occurs, the wave doesn't pick one, it sort of splits. We often say the universe splits, but more precisely, the universe's state branches into mutually isolated branches. Each branch is a world where one outcome happened. They don't interact after splitting, which is why we don't see crazy interference effects in daily life. The branches effectively ignore each other. This is where quantum decoherence comes in. It's the physical process that makes distinct outcomes behave like separate, classical realities by rapidly scrambling any interference between them. You can imagine decoherence as the environment, air molecules, light, everything around, constantly measuring small systems, which locks in outcomes and destroys the delicate quantum superpositions on large scales. As physicist Wojciech Zurek describes, the environment monitors certain stable states. He calls them pointer states, and wipes out the others via decoherence. What's left in each branch are those robust, classical-like states, like our live cat or dead cat scenarios, that don't interfere with each other anymore. Thus, each branch appears to have a single outcome, and the other outcomes are effectively invisible, safely tucked away in other branches. All of this might sound extravagant, an ever-multiplying myriad of worlds, but it uses the same basic quantum rules we know, with no extra collapse mechanism. Some proponents even bristle at the term interpretation for many worlds. The physicist David Deutsch famously said, "Calling many worlds an interpretation is like calling dinosaurs an interpretation of fossil records." In other words, he sees the branching multiverse as the straightforward reality that the equations are telling us, not a speculative add-on. Whether you agree or not, this highlights that many worlds isn't introducing new equations, just a new mindset. The math says all outcomes happen, so let's believe it. Now, let's step back. As promised, no hype and no certainties. Many worlds is a plausible interpretation, not proven fact. It has a growing number of supporters in the physics community and is considered a mainstream interpretation among others, but it's far from a settled truth. Some find it elegant and inevitable. Others find it extravagant or even absurd. Our goal here isn't to sell you on many worlds. It's to explore a consequence that flows from it, something profound and unsettling that has been dubbed quantum immortality. But to grasp that, we needed this foundation, the idea that reality might branch at every quantum juncture, and that you, as a conscious being, would have multiple future selves across these branches, experiencing different outcomes. So hold on gently to that picture. A vast, ever-branching tree of realities, each with a version of you. You, the listener, are like a traveller reading one page of a choose-your-own-adventure story, unaware of the pages you didn't read. But in many worlds, those unread pages are still written, still out there, being read by another you. Now we can ask, what does that mean for life and death from your point of view? Act 2. Many Worlds, explained like a lullaby. Close your eyes for a moment. Picture a quiet library at midnight. Endless shelves vanish into darkness. Each book on the shelf is a story of a life, your life. On the spine of one book, your name and the dates born, year, died, year. But next to it, another book, same name, slightly different death date, or perhaps no death date at all. Book after book, row after row, each one a different version of how your story could go. It's a library of forking paths. In this gentle metaphor, the many worlds interpretation is like that library. Every decision, every chance event, every quantum coin flip in your cells or in the stars creates a new book, a new branch of the story. You are the reader, or rather, one of the readers. You can only experience one story at a time, one continuous narrative that feels like your life. You move from page to page, unaware that at certain points the story could have split. You don't get to read the parallel chapters. They sit quietly on the shelf, read by versions of you that branched off. Jorge Luis Borges, the writer who loved paradoxes and labyrinths, imagined something like this in the Garden of Forking Paths. In that story, a man discovers an ancient novel that is also a maze. Whenever a protagonist faces a choice, he doesn't choose one path. He chooses simultaneously all of them, creating various futures that branch and branch again. In one branch, the hero dies. In another, he lives. In another, he triumphs, and so on. The novel was baffling to readers because it was filled with contradictions. How could all these incompatible plot lines coexist? Only when you realize it's a branching story, a forking path through time, does it make sense. Every fork is taken, nothing is lost. It's just that each reader's experience follows one fork and not the others. Many Worlds says, reality itself might be written in that forking style. Every quantum event is a silent split, but unlike a physical library, these branches are not sitting on shelves in space. They are, in a sense, stacked on top of each other in the same space, but unable to interact, like ghostly layers or parallel streams of time. We call them parallel universes, loosely, but they're really just this universe unfurling in all possible ways. Now, this sounds grandiose. Infinite worlds, infinite copies. To lullabyify it, let's shrink it to something tangible. Imagine you have a single quantum coin. You're about to toss it. According to quantum mechanics, before you look, the coin's state is a superposition. Not heads or tails, but a mix of both. When you look, in many worlds, the universe splits. One branch where it landed heads, one branch where it's tails. Two universes, identical up to that moment, now diverged. In one, you're celebrating a lucky flip. In the other, you're maybe frowning. Each of you feels like a complete, continuous self who just saw a result. Now multiply that by all the billions of quantum interactions happening every second, everywhere. Branches proliferate constantly. But don't worry, we're not drowning in chaos. Decoherence ensures that each branch might as well be its own classical world. Most branches differ only microscopically and remain unnoticed. Once in a while, a branch diverges in something noticeable, like whether a car crash happened or was narrowly avoided. Think of the branches like a great tree, and your consciousness is like a little bird perched on one branch. You can hop to a neighboring twig without noticing anything. That's analogous to all the tiny quantum outcomes that don't drastically change your experience. But you can't hop between big branches once they've split. There's no route to a radically different outcome where, say, an accident occurred that you didn't experience. Those branches are now separate trees in the forest of the multiverse. Another analogy. It's as if every moment the world copies itself and updates the copy for each possible outcome. It's not quite creation from nothing. It's just the world's wave function, naturally expressing all outcomes. We use imaginative language like splitting or copying, but the underlying math is just one wave function evolving. Still, from inside, it feels like copies. You might imagine a calm mirror hall, where each mirror reflects a possibility. When a quantum event happens, it's like stepping into the hall. Suddenly, there are two reflections of you, each going a different way around a pillar, and once they part, they can no longer see each other. The lullaby here is that none of this is science fiction in the equations. It's one interpretation of very real physics. If it's true, it doesn't produce new crazy phenomena like time travel or communication with other universes. It mostly just produces a lot of silent parallel existence. Everything you experience remains consistent and stable. The weirdness is all in the unseen, that there are other yous in other tracks, also thinking they are unique. And now, softly, arises the question. If among those countless branches, there are some where you live and some where you die, what is it like to be you? You obviously can only continue thinking in the ones where you're alive. That sounds trivial. Of course, dead people don't think. But follow that triviality into the heart of many worlds, and you get something deeply non-trivial. From your subjective perspective, you might only ever experience being alive. Even if, objectively, there are branches where you died, you are not there to know it. You are always the one that survived, simply because only survivors have a continuing perspective. This is the crux of the eerie idea we're exploring. It's not about magical immortality or souls hopping worlds. It's about a selection effect. Out of a vast library of branching stories, you only read the ones that aren't cut short. If that library is truly vast, maybe even infinite, with branches for every possible narrow escape, then it suggests a kind of guaranteed continuity of experience. Not for all of you. Most of you in other branches might die normally, but for at least one thread of you that beats the odds every time. That thread would experience something like quantum immortality. Time to put a name to this unsettling notion. Quantum immortality. This concept emerges from a famous quantum thought experiment often called quantum suicide. Don't be alarmed by the term. This is purely a theoretical exercise, not something anyone should ever attempt. In fact, physicists who discuss it always stress how foolish and dangerous it would be to treat it as more than a thought experiment. So, strictly as a mental experiment, here's the setup. Imagine a device like Schrödinger's deadly box, but you're the one inside. The box is rigged such that every time you press a button, it measures a quantum coin. There's a 50% chance it instantly kills you, and a 50% chance it spares you. You have it set to run this test repeatedly, say, a gun that triggers or not, based on a quantum event, each time you pull the trigger. Now, according to ordinary common sense, and interpretations of quantum mechanics like Copenhagen, your chances of surviving many rounds of this are astronomically low. Maybe you survive the first trigger pull, maybe even beat the odds a few times, but eventually the deadly outcome happens, and that's the end. That's what an external observer would expect. After many attempts, almost certainly the person in the box is dead. But Many Worlds says something different. On each trigger pull, reality splits. In one branch, you die. In another, you live. After one round, there is at least one branch where you're alive. After 2 rounds, there's at least one branch where you survived twice in a row. After 100 rounds, there's at least one branch, as insanely unlikely as it seems, where you survived 100 times. As the number of trials goes to infinity, Copenhagen says your survival probability goes to 0. But Many Worlds says there will always be some branch in which you continue living, no matter how many rounds. Each time, the you that's alive is guaranteed to find themselves in the branch where the coin came up safe side for them. The you that gets the deadly outcome is gone and doesn't experience anything anymore. So from your first-person perspective, you only experience the sequence of events in which you never died. Even if that sequence is astronomically improbable, it exists in the multiverse, and that's the one you'd be aware of. In a sense, under Many Worlds, your survival through all iterations is physically necessary, because all possible outcomes happen, and the only ones you can know about are the ones where you're still alive. This is the essence of quantum immortality. The conjecture that if Many Worlds is true, you might subjectively never experience death. Every time you face a fatal quantum coin flip, whether it's a gun, a car accident, an illness, there will be some branch of the wave function where, against all odds, you survive. And that's the only branch you can be aware of after the fact, because in all the others, you're not there to witness anything. So it will feel to you as if you're somehow extraordinarily lucky every time. No matter how low the objective chances, you'll always find yourself beating the odds, because the only alternative is that you wouldn't find yourself anywhere at all. It's a selection effect plus first-person bias. Objectively, from a God's eye view, you die in many branches. The vast majority of branches you perish when you should, by probability. But from the inside view, you are like a strange immortal. You go on, because you're always in the surviving branch, by construction. This thought experiment was articulated in different forms by several thinkers, and later popularized in physics discussions. It remains a thought experiment because, as an actual test, it's not practical or ethical. It's essentially unobservable except to the one participant. And we prefer not to gamble human lives on physics interpretations. Now, outside of contrived labs, people have wondered if this applies to everyday life. They dub that quantum immortality, the idea that any time you might die, there's some branch where you don't, so you, the conscious you, just keep trucking along, bouncing between all those lucky branches indefinitely. If you take that to its extreme, you might never experience your own death. The world around you might thin out, but your chain of perception never includes a full stop. Before we get carried away, let's note, This is highly speculative, and even supporters of many worlds are divided on it. One major reason is that the thought experiment assumes a very binary, quick death, a clean quantum event that either kills you or leaves you completely unharmed. Real life usually isn't like that. Death is more often a continuum, not a coin flip. In a car crash, there are many gradations of injury. Consciousness can fade gradually. There isn't always a simple alive or dead switch. So even if many worlds is true, you might not get a neat branch where you simply walk away from what should have killed you. Instead, you might get branches where you are mortally wounded, but technically alive longer, or in a vegetative state, branches where you effectively cease, even if a pulse lingers. So the quantum immortality idea is controversial and not universally accepted, even among many worlds enthusiasts. Some argue it's a misuse of the theory, a tempting but ultimately flawed line of reasoning. To really evaluate it, we should look at objections and caveats that smart people have raised. That's our next act, a reality check. Act 4. The objections. This is where we earn our keep, by questioning the very idea we've been spinning. Let's ground this in healthy skepticism and clarify the pitfalls. If your mind has been seduced by the quantum immortality notion, this is where we gently apply the brakes and look at why that might be very wrong. Objection 1. Many worlds is not proven. Quantum immortality rests entirely on many worlds being the correct picture of reality. But we don't actually know that. It's a plausible interpretation, yes, consistent with current data, but so are other interpretations. If many worlds isn't how nature works, then quantum immortality doesn't even get off the ground. Objection 2. Survival is not binary. The real world has many shades of grey between alive and well and stone dead. Even if your body survives, you might lose so much cognitive function that effectively, from your perspective, it's as if you died. Consciousness is an emergent process of many parts of the brain, and those parts can fail gradually. Immortality, if it were to happen this way, might not feel like living forever. It might feel like slowly dissolving. Objection 3. Probabilities still matter. In many worlds, branches carry different weights that behave like probabilities. A branch with tiny weight is one you're vastly unlikely to find yourself in. Quantum immortality reasoning often assumes you can ignore death branches because you won't observe them. But many philosophers and physicists argue you should still expect outcomes in line with normal probabilities, which means you should still strongly expect to die in a deadly gamble. Objection 4. The which you problem. If reality branches into one version where you live and one where you die, there isn't a single continuity that magically hops into the live branch. There are two future copies. One ends, one continues. Saying you will definitely survive can sneak in an image of a soul jumping tracks, but many worlds doesn't include that. It includes duplication and divergence. The word I becomes slippery in a branching scenario. This leads us to identity questions. Some philosophers argue personal identity isn't a single immutable thing. It's continuity and connection. In many worlds, each branch's you has continuity with the pre-split you, but from the moment of split onward, they are separate persons. The fact that one dies doesn't transfer their consciousness to the other. There is concurrently another conscious line that was a duplicate up to that point, which goes on. Does that count as you surviving? Or a twin who branched off at the last instant? Objection 5. It might not be immortality in any pleasant sense. Even if you never experience being dead, that doesn't mean you experience health or youth. You could grow old, suffer, waste away, just never quite reach the clinical endpoint. Immortality might be a curse more than a blessing, survival without quality, purpose, or relief. Objection 6. Consciousness might not work that way. Quantum immortality requires assuming that every physically possible near-death escape not only exists, but that your consciousness will always find itself in one of them. But minds are processes. Brains can be damaged. At some point, consciousness might not be there to continue, even if the body is technically alive. These are open questions at the seam of physics and the philosophy of mind. At this point, virtually all experts, even those who love many worlds, conclude that quantum immortality is not something to bank on. It's a thought experiment highlighting a strange implication, not a promise of eternal life. Winning the survival lottery doesn't help all the other versions of you who didn't. And from an outside perspective, that's most of them. So our credibility anchor is simple. Quantum immortality is not an established scientific fact. It's a provocative philosophical consequence of many worlds, if you take it to its extreme and adopt a certain observer-centric reasoning. Many worlds could be true, and quantum immortality still false or irrelevant. As with all deep questions at the seam of physics and subjectivity, we tread carefully. Now that we've tempered things, let's entertain two imaginative pathways, one dark and one tender. These aren't scientific per se, they're more like story variants. If quantum immortality were true, what might it feel like? And whether or not it's true, what emotional insight might we glean from contemplating it? Act 5. The horror variant. So let's play what if in the darkest way. Suppose quantum immortality is how your life goes. You, right now listening to this, are someone who will never subjectively die. Sounds great? Well, let's follow it through. In this scenario, whenever death comes knocking, you always slip through its fingers. The branch of the multiverse where you survive is the one your mind will find itself in. At first, that might mean narrow escapes. The gun misfires. The car just misses you. You wake up from a deadly illness miraculously cured. You feel lucky, blessed even. Perhaps you think you're invincible, but danger keeps coming, as it does for all mortals, and as the years roll on, the probabilities get slimmer. Maybe by age 90, you've already survived a few close calls that statistically you shouldn't have. To your loved ones in this branch, you're an amazingly fortunate person. But fortune has a flip side. What about the next threat? As probability keeps thinning, the scenarios required for you to survive might become more extreme. The world around you contorts to keep you alive. If you fall from a plane, maybe you land in just the right snowbank, and just the right medical team finds you. If you get a disease that's almost always fatal, you'll be the 1 in a million that reverses. It's exhilarating in movies, but imagine it happening not once, but over and over as your only path. Soon, you might notice something. The world you inhabit grows stranger. To keep you alive, very implausible things have to keep occurring. You're the soldier who never dies in battle while all your comrades fall. You're the crash survivor who walks away while all others perish. At some point, it's beyond luck. It's uncanny. And awful they may become. Survival is not the same as wellness. You survive, but barely. You live on, only to face another catastrophe. You survive that with further injuries. Disease ravages you, but never quite kills you. You just linger, reduced. Immortality becomes a narrowing corridor, not shining cities and infinite knowledge, but endless near death. Picture being far older than you should be. Organs failing, constant pain, hooked to machines, yet you cannot die. To any external observer, it's a miracle every time. To you, it's a curse. You've become an immortal in hell. Not a literal hell, but a state of perpetual survival without relief. If you take the logic all the way, as long as physics doesn't make something strictly impossible, there might be some branch that allows awareness to persist in bizarre forms. in strange environments, in improbable conditions. The timeline becomes a thread pulled tighter and tighter, thinner and thinner, but never fully snapping. Now, let's breathe. That was bleak. Remember, this is a speculative nightmare scenario, not an established fate. Many physicists argue it won't actually happen in real life, because consciousness fades, because death isn't binary, because the assumptions break. We explored it to feel the weight of the idea, the seduction of "I can survive anything" turning into "I might survive everything." Oh no. The purpose of painting this horror variant is not to depress you, but to confront the seduction of quantum immortality with its dark side. It asks, are you sure you want to live forever? And it forces a kind of quiet gratitude for ordinary endings, the mercy of a life that can complete, not merely continue. Act 6. The tender variant. Maybe quantum immortality is just wrong, or maybe we'll never know. But even entertaining it shines a light on something real, the sheer fragile miracle of being alive at all, right now. Instead of making us feel invincible, it can make us feel humbled. Think of all the coincidences and chance events that had to go just right for you to be here. Not just avoiding death, but even the chance to be born, the chain of meetings, timings, and near misses that assembled you. In any one life, there are so many junctions where things could have gone differently, yet here you are, experiencing this moment. It's a bit anthropic. Of course you're here to notice it. Otherwise, you wouldn't be noticing anything. But that doesn't diminish the wonder. It enhances it. It's saying, out of all the possible stories, this is the one you get. Whether or not there are others is almost beside the point. What matters is this branch is yours, and it's unique. The quantum immortality idea highlights something subtle. You never actually experience not being here. All you ever experience is being. One day, presumably, you won't have moments, but you'll never know that. So in a way, subjectively, your life is your entire universe. That can be scary, or it can be freeing. It means right now is everything. And it's a gift precisely because it isn't guaranteed to continue indefinitely. Even if there are countless versions of you, it doesn't cheapen the choices and moments you live. If anything, it makes each one more precious, because you only get to walk one path. This cup of tea, this breath, this small, ordinary morning, it's yours alone in this branch. And there's a strange comfort here. You don't experience being dead. The fear of death is often a fear of the unknown nothingness, but death, when it comes, is not a place you visit. You don't meet it as an experience. You only experience life, until you don't. That reframing doesn't grant immortality. It grants a softer relationship with finitude. We can also draw a caring lesson. Your loved ones exist in their own fragile threads too. In some branches, perhaps, loss happened sooner. In this one, it didn't. At least, not yet. That doesn't make this world less real. It makes it more urgent to cherish. Not in panic, in presence. So while the horror variant emphasizes the curse of endless survival, the tender variant emphasizes the blessing of improbable life. Awe and unease can both point to meaning. They meet in the middle, here, now. This quiet moment, alive, aware, together. Maybe, in the grand scheme, it doesn't matter if there are infinite versions of you or just one. What matters is that this version is real, and real for only a brief time. You are confined to your story. But that confinement is beautiful, like the way a poem is confined to its lines, or a song to its notes. It gives shape to your life. Sitting with that thought can bring a kind of tender peace. Awe, unease, and meaning swirl together. The appropriate response is perhaps a gentle, mindful breath and a quiet thank you. Thank you to chance, or the universe, or whatever you call it, for this branch, this life, this heartbeat. Act 7. Final transmission. If there are indeed infinite versions of you, why are you here, in this one, listening to these words right now? Perhaps you'll never know. Perhaps the question is the answer, to awaken a new way of seeing your own life. This has been a quiet journey through one of the strangest what-ifs in physics and philosophy. No certainties, only gentle experiments in thought. Sometimes, just contemplating such things changes us, leaving us with a slightly different sense of what it means to say, I am here. Subscribe to Dark Beacon for more of these quiet explorations of reality's deep, dim corners. Until next time, take care. In every branch of the multiverse, take care of yourself. Multiverse, take care of yourself. It's late. The world around is quiet, almost still. In this moment, something quietly extraordinary is happening. I'm aware. You're aware. We seldom stop to think about it, but the simple fact of being conscious, of experiencing anything at all, is nothing short of a miracle. Notice it for a second. The gentle rise and fall of your breath, the faint sounds in the distance, the thoughts drifting through your mind. There is an experience of all this, a private inner world that only you can truly know. This everyday awareness is so fundamental to us, yet so mysterious. Why should there be this inner light behind our eyes? Why do we have this first-person viewpoint, the feeling of being you, right here, right now? Science can describe the body and brain in exquisite detail. Neurons firing, chemicals flowing, signals flashing. But none of that description from the outside fully captures what it's like from the inside, to be you. Your warmth, your aches, the bright colours and rich sounds you perceive, the very feeling of existence. These are experiences, not just measurements, and no instrument can detect them directly. If someone looks at your brain activity, they might see patterns on a scan, but they won't see the blue of the sky that you see, or feel the sweetness of the music that you hear. That gap between what science measures and what we directly experience, that is the strange fact of consciousness. Each of us carries a whole universe of sensations and thoughts inside, utterly real to us, yet invisible to anyone else. In a way, each of us is a tiny miracle, a collection of atoms that somehow woke up and now contemplates itself and the world. How does that happen? Why does it happen? These questions softly hang in the air as we sit here in this still moment. They have no easy answers. For now, just notice the reality of being aware. Feel the presence of your own mind, quietly observing, quietly being. Let that wonder settle in. Before we go any further, before any talk of physics or theories, let's just acknowledge this profound mystery we carry with us. We are conscious. We don't know why or how, not fully. It's okay not to know. For a moment, simply rest in the quiet fact that you exist, that something is here, right now, behind your eyes, listening. This gentle curiosity, this reflective calm, we'll carry it with us as we explore deeper questions. No rush, no alarm, just the soft glow of awareness, illuminating a path into the unknown. A world made of equations. Imagine, for a moment, the viewpoint of classical physics, the physics of Newton, of a clockwork cosmos. In this view, the universe is like a perfectly operating machine. Every piece of matter, from planets to particles, follows precise mathematical laws. If you know the starting conditions and the laws, you can, in principle, calculate everything that will ever happen. It's orderly, reliable, even elegant, a world made of equations. In such a universe, an observer is irrelevant to the fundamental story. The apple will fall from the tree whether or not anyone is there to watch. The moon circles the earth circles the sun, all according to gravity's pull, completely independent of any mind considering it. Reality, in this classical picture, is out there, objective and solid, and we are just spectators, peering in from the outside. This idea can be comforting in its clarity. There is a definite world that exists on its own terms. A rock is a rock. It has a certain mass, a certain position, a trajectory, all of which can be measured, or not, without changing what the rock is doing. To measure something in classical physics is simply to look at it, to read what is already true. We might disturb it slightly with our instruments, but in principle the properties were there all along, waiting to be found. Nothing is fundamentally mysterious about observation. It's just shining light on the gears of the clockwork. By the late 19th century, scientists had grown confident in this clockwork view. Some even imagined that soon we'd know nearly everything about how the universe runs. There was a sense that physics was almost complete, just a few loose ends to tie up. But those loose ends began to unravel the whole tapestry. As the 20th century dawned, experiments started revealing cracks in the classical picture. Tiny things, atoms, electrons, photons, were not behaving like neat little clockwork pieces at all. The equations that had worked so well for planets and billiard balls suddenly struggled to explain the strange new observations. Reality was about to show a different face, one that wasn't solid and certain, but fuzzy and full of possibilities. The comfortable idea of an objective world that didn't need an observer was about to be upended by a new theory, one that would force us to ask what it means to observe anything at all. That theory was quantum mechanics, and when it entered the room, the universe, in a sense, stopped behaving like a thing, and started behaving like a question. Quantum mechanics enters the room. Quantum mechanics arrived like a whisper of something completely new. It told us that the smallest pieces of nature do not behave like solid little rocks at all. Instead, they act more like waves of possibility. An electron, for example, doesn't have to be in one specific place. It can exist in a hazy superposition, as if it's spread out in many places or states at once. Only when we check, when we perform a measurement, does the electron seem to pick a definite location or state to be in. This was a radical departure from the clockwork universe. In this subatomic realm, we deal in probabilities, not certainties. We can no longer say, the particle is right there, moving this fast. Instead we say, if we look for the particle, there's a chance we'll find it here, and a chance we'll find it there. We trade the solid predictability of classical physics for a kind of statistical dance. Reality, at least at tiny scales, seems to remain ambiguous until a question is asked. Imagine asking nature a question. Where is this electron right now? Quantum mechanics says nature won't give you an answer until you ask. And when you do ask, by measuring, the answer you get is somewhat unpredictable. You might get this result or that, with only the odds known beforehand. It's as if the universe holds multiple possibilities in suspense, and your measurement coaxes one into reality. This idea can feel unsettling. One of the greatest physicists, Albert Einstein, famously protested, "God does not play dice." He disliked the notion that fundamental physics involves chance. Yet experiment after experiment has shown that this probabilistic description is accurate. At the fundamental level, nature does seem to play dice. If you set up the same experiment in the same way, quantum theory says you'll get a spread of different outcomes, each occurring randomly, but with predictable probabilities over many runs. So what changed with quantum mechanics? The universe stopped behaving like a straightforward, objective thing, and started behaving more like a series of questions and answers. Particles no longer had strictly defined properties that we merely observe. Instead, the act of observation itself became tangled up with what can be known. Light can act as a particle or a wave, depending on how we look at it. An electron can seem to go through two holes at once until we peak, and then it appears to have gone through just one. The very framework of reality now had a curious role for the observer. You don't just read off nature's properties. In some way, you help determine them by the very act of inquiry. It's important to emphasize, this doesn't mean mind over matter in any magical sense. It's not that our whims change the world arbitrarily. What it means is that at microscopic scales, to observe is to interact, to ask nature a question. And nature's response isn't a pre-written fact sitting out there independent of the question. Instead, the question shapes the answer you get. Quantum mechanics doesn't give us a simple picture of a world that just is. Instead, it gives us a kind of conversation with the world. We ask, nature answers, and only then does a particular reality crystallize out of the many possibilities. This was like nothing physics had seen before. The ground felt shaky under our understanding of reality. What exactly does it mean to observe something? Why should looking or measuring affect how things are? These questions lead us right to the heart of quantum mechanics' deepest mystery, the measurement problem. The measurement problem. All of this leads us into one of the deepest puzzles in quantum physics, the measurement problem. Put simply, it's the question of what exactly happens when a quantum possibility becomes a concrete reality. Quantum theory gives us two very different rules for how things change. When nobody is measuring, a particle is described by a wave function, a kind of mathematical wave that evolves smoothly and encompasses all the possibilities of what the particle could be doing. But when a measurement occurs, that wave suddenly collapses to a single outcome. It's as if nature abruptly picks one of the many threads and says, "Here is what happened, this is now real," and the other possibilities fall away, at least from our view. This raises a profound question. What counts as a measurement? When and how does that collapse actually happen? After all, if everything is quantum, you could say the measuring device, say a Geiger counter detecting an atom's decay, is also made of atoms and could become just another part of a larger quantum system. By that logic, the Geiger counter would get entangled with the atom, and now it would be in a superposition of detected decay and didn't detect states. If no one looks at the counter, is it in limbo, both clicked and unclicked? Do we then need a person to look at the device to collapse that state as well? This line of thinking can lead to absurd scenarios. The most famous is Schrödinger's cat. Physicist Erwin Schrödinger imagined a cat sealed in a box with a cruel quantum device, a tiny radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and breaks the vial, killing the cat. If the atom doesn't decay, the cat lives. According to quantum theory, until we open the box and check, the atom was in a superposition of decayed and not decayed. So the cat would seemingly be in a superposition of alive and dead at the same time. Schrödinger meant this thought experiment as a criticism, a way to say, look how ridiculous this is if we extend quantum rules to everyday objects. It dramatizes the measurement problem. Where does the quantum indeterminacy end? Does it stop at the atom, the detector, the cat, or only when a human opens the box and observes what happened? In the real world, we don't see cats that are alive and dead. Something obviously resolves the ambiguity long before it reaches that scale. Many physicists would argue that interactions with the environment effectively perform a kind of measurement on the cat's situation, collapsing the possibilities without a conscious observer. This idea, known as decoherence, suggests that fragile quantum superpositions get destroyed as they interact with the messy, noisy environment, ensuring that by the time we look, the cat is definitely one way or the other. But even decoherence, while it explains why superpositions are hard to maintain for big things, sidesteps the core puzzle. What fundamentally is a measurement? Is it any interaction that entangles a system with its surroundings? Is it an irreversible recording of a result? Or is it only when a mind becomes aware of the outcome? Physicists and philosophers have wrestled with this for a century. Some early interpretations of quantum mechanics even flirted with the idea that consciousness might be the special ingredient that collapses the wave function. That is, the universe would decide the fate of Schrödinger's cat only when a conscious observer opened the box and looked. This idea is provocative, to say the least, and we must be very careful with it. It's not a claim proven by experiments, but rather one way to try to make sense of things. We'll explore it and other ideas, but keep in mind, no consensus exists on this. It's called a problem for a reason. For now, we're left with a haunting image, reality in waiting, like a coin balanced on its edge, tipping one way only when someone observes. The measurement problem is the open question at the heart of quantum mechanics, a question about questions. Why does asking what happened at the quantum level seem to create a definite answer? Or does it? In this uncertainty lies a boundary, a place where our understanding frays, and on one side of that boundary stands the observer. It's time to ask, what do we really mean by an observer? Who or what counts as one? The observer, human, device, or something else? So, who or what is an observer in the quantum sense? This turns out to be a surprisingly slippery question. In everyday language, an observer sounds like a person, someone who observes. In quantum experiments, however, the observer could be a measuring instrument, a Geiger counter, a camera sensor, a piece of photographic film. These devices aren't conscious, yet they can certainly register outcomes. A Geiger counter clicks in response to radiation. It doesn't have a mind, but it has effectively observed a decay by recording it. Many physicists would say that any physical interaction that irreversibly records information counts as an observation. By that view, the universe is constantly observing itself through countless interactions. Particles bump into each other, light hits dust, atoms interact. These are measurements too, in a broad sense, collapsing possibilities into specific outcomes all the time. In this picture, the cat in Schrödinger's thought experiment doesn't actually remain in a spooky limbo, because the moment the Geiger counter detected the atom decay, or didn't detect it, the outcome was decided. Yet, a nagging question remains. If a tree falls in a forest with no sentient being around, does it make a sound? Most would say yes, of course. The air vibrates, the ground shakes. The universe doesn't need a person to be there for events to happen. Similarly, it's hard to imagine that before any life existed, the cosmos waited in indeterminacy. Galaxies collided, stars were born and died, all without any conscious witness. So it seems reasonable that observation is happening at a fundamental level through physical interactions, not requiring a mind at every turn. Why, then, do we even bring consciousness into this discussion? The reason is partly historical and partly philosophical. Historically, some early thinkers, including the physicist Eugene Wigner, wondered if maybe conscious awareness is the final key that turns a potential outcome into an actual one. Wigner imagined a scenario now famous as Wigner's friend, where one observer measures a quantum event and sees a definite result, but another observer might consider the entire lab and friend to be in a superposition of different outcomes until told the result. This leads to a strange recursion. Does the wave function collapse for the friend who witnessed it, but not for Wigner outside? Wigner's suggestion was that when the result becomes conscious knowledge for someone, the collapse is complete. Wigner eventually backed away from this interpretation, and most physicists don't think we need to invoke consciousness to explain quantum experiments. After all, we can build automated detectors that record particle behavior without anyone watching in real time, and the predictions of quantum theory still come out right. A video camera will collapse the wave function of a photon just fine by absorbing it and recording a dot on a screen, even if no one looks at the tape until later. And yet, there's something unresolved. We know how to calculate what happens in an experiment, but we're still not entirely sure what counts as the dividing line between quantum uncertainty and concrete reality. Is it the moment a particle hits a detector, or the moment the detector's data is read out? Or is the distinction ultimately an illusion, with everything being quantum and our sense of a single reality emerging only because we, as observers made of quantum stuff, are entangled with one particular outcome? It can make your head spin. Perhaps observer is just a convenient word for any system that interacts and acquires information. Or perhaps observation in the full sense requires consciousness, a viewpoint to whom the information matters. At this point, science leans heavily to the former, but the truth is, we don't have a final answer that shuts the door completely on the mystery. So we are left with ambiguity. A detector, a person, a planet. Each can be thought of as observing in some way. Does one of these fundamentally differ from the others? We don't know. Interpretations of quantum mechanics, gently. Over the years, to make sense of quantum mechanics and its puzzling relationship with observers, scientists have developed several interpretations, essentially different stories we tell ourselves about what is really happening behind the math. Importantly, these interpretations all use the same equations to predict the outcomes of experiments. They only differ in how they describe reality under the hood. None of them has been definitively proven over the others. The Copenhagen interpretation says, "Don't ask what happens before you measure. The theory speaks about what we can observe. The wave function is not necessarily a physical wave. It's a tool for calculating probabilities. When you measure something, the wave function collapses because that's the moment reality yields an outcome. What caused the collapse, or whether the particle had a definite reality before measurement, is not answered, and the Copenhagen spirit often implies that asking about an unmeasured state is meaningless. It's pragmatic. Use the theory to get numbers, but don't worry too much about the metaphysics. The many worlds interpretation, proposed by Hugh Everett, says, what if the wave function never collapses at all? Instead, whenever there's a quantum event with multiple possible outcomes, the universe splits into branches, one for each outcome. In one branch, the cat lives. In another, the cat dies. Every possible result happens, but in different copies of the universe that diverge and do not interact. From our perspective, it looks like collapse because we only experience one outcome, one branch. Many worlds removes randomness at the moment of measurement, but at the cost of imagining an enormous number of parallel worlds. Objective collapse theories add a new physical rule. Wave functions do collapse, but not because of observers. Collapse is a physical process that happens on its own, under certain conditions. GRW suggests a tiny, spontaneous collapse probability for each particle, which becomes effectively immediate for large objects. Roger Penrose has suggested gravity might trigger collapse. These theories are intriguing because they can make testable predictions, but so far experiments haven't confirmed deviations from standard quantum mechanics. Information-based and relational views pivot to knowledge and relationships. Cubism treats the wave function as an observer's degrees of belief, updated at measurement. Relational approaches suggest properties are meaningful only relative to a system interacting with another system. A measurement is just an interaction establishing a relationship. There are other ideas too, like pilot wave theory, which restores determinism by having particles with definite positions guided by a hidden wave. The key point is, no one interpretation has won the day. Quantum mechanics works extraordinarily well as a predictive tool, but what it means about reality is still up for debate. Some physicists stick to shut up and calculate without losing sleep over it. Others explore interpretations in search of conceptual clarity or hints of new physics. For our calm, late-night inquiry, what matters is that the role of the observer ranges from nothing special, just part of the system, to central and necessary for reality to take shape. No one has the final answer, and that's okay. We hold these interpretations lightly, like different colored lenses through which to view the quantum world, knowing each lens highlights some aspects and obscures others. And after all of this, one question keeps creeping back in. What about consciousness itself? We've been considering how it might play a role in physics, but we haven't asked the flip side. What is consciousness, and could quantum physics help explain it? Where consciousness sneaks back in. Even if we set aside the idea that observation might influence quantum events, there's a more basic mystery. Why does consciousness exist at all in a universe described by physical laws? Physics deals with what can be measured objectively. It gives us marvelous equations to predict how particles move, how stars shine, how neurons fire. But nowhere in those equations can we find a single term that explains experience. The feeling of being, the redness of red, the taste of salt, the ache of sadness, or the thrill of music. Physics can tell us what patterns correspond to the music you hear, but it remains silent on how those physical events become the rich, private experience of actually listening. This is often called the hard problem of consciousness, explaining why and how physical processes in the brain give rise to subjective experience. We can map correlations between brain states and reported experience, but even a perfect map still leaves the question. Why is there a subjective feeling at all? Why aren't we just complex biological robots with no inner life? Yet here we are, undeniably experiencing the world. It's as if reality has an extra layer that science hasn't fully incorporated, the first-person layer, the world of consciousness. We can point to brain regions and describe processing, but that description doesn't capture what it feels like to see a sunset. Some argue consciousness is an emergent property of complexity, that when neurons fire in the right way, experience simply happens. That might be true, but it still feels like the lights turning on without an explanation. So we have two mysteries side by side. The quantum world, where observation blurs the line between question and answer, and the conscious mind, where subjective experience resists objective capture. It's natural to wonder if these mysteries are related. Over the years, some thinkers have tried to link them, suggesting that maybe the weirdness of quantum physics offers a clue to how awareness arises. It's delicate and speculative terrain. Many scientists are skeptical of combining two unknowns and expecting a solution. It's easy to slide from careful reasoning into wishful thinking. Still, the question persists. Could consciousness be tapping into quantum processes in some way? Might the foundations of physics and mind be intertwined at a deep level? We don't have definitive answers. What we do have are hypotheses, intriguing, controversial, and uncertain, that venture into this territory. Quantum mind hypotheses, careful and slow. One of the most well-known ideas comes from Roger Penrose and Stuart Hameroff, orchestrated objective reduction, or ORC-OR. They propose that inside neurons are microtubules, and that these structures might support quantum processing, perhaps tiny quantum computations in the brain. In their view, quantum states in microtubules could become entangled and enter superposition, then collapse in a way tied to moments of conscious awareness. Penrose has also argued that consciousness might involve processes that are non-computable, beyond standard algorithms, and he has suspected quantum gravity could be involved. It's a bold idea. If true, it would mean consciousness is rooted in quantum events, perhaps tied to fundamental physics, but it's highly controversial. A major objection is that the brain is warm, wet, and noisy. Delicate quantum states tend to decohere quickly in such environments. It's hard to maintain quantum coherence except in carefully controlled conditions. The inside of a neuron at body temperature seems like an unlikely place for long-lived quantum superpositions that could influence neural firing. Some calculations, such as those by Max Tegmark, have suggested any such quantum superpositions in microtubules would decohere on timescales far too short to matter for neural activity. Critics argue neurobiology explains brain function without quantum computation, and that there is no need to invoke quantum effects unless evidence demands it. OR has not been empirically demonstrated. There has been ongoing interest, including questions about whether anesthetics interact with microtubules in ways relevant to consciousness, but no clear proof has emerged that quantum states in microtubules are the key to awareness. Still, nature can surprise us. Quantum biology has explored cases where living systems might use quantum effects, such as coherence in photosynthesis, or proposed quantum mechanisms in animal navigation. These examples show quantum phenomena can appear in biology, though the brain is vastly more complex and active than those systems. Beyond OR, some speculate quantum uncertainty might contribute to indeterminism connected to free will, or that entanglement is analogous to the unified nature of conscious experience. These analogies can be suggestive, but analogy is not evidence. The overall scientific consensus remains that there is not solid evidence for quantum processes driving consciousness. The appropriate stance is curiosity tempered with skepticism. Consciousness as fundamental, a philosophical turn. Now we open the door to another possibility. What if consciousness isn't something that emerges out of matter, but a fundamental feature of reality? This goes beyond what science can currently test, but it has gained attention among philosophers of mind and some scientists. In physics, what we consider fundamental has shifted before. Time and space became unified and relative. Matter and energy turned out to be two forms of the same thing. Some have suggested information might be as basic as physical stuff. So could consciousness be like that, intrinsic to existence, rather than an accidental byproduct? One expression of this idea is panpsychism, the view that consciousness, or at least some basic form of experience, is a fundamental feature of matter. This doesn't mean tables and rocks have thoughts like we do. It suggests the basic constituents of those objects might have unimaginably simple proto-experiences, and that complex organization, like a brain, somehow gathers these into the rich consciousness we know. Another related idea is neutral monism, that the fundamental stuff of the universe is neither mental nor physical, but something more basic that underlies both. On this view, what we call physical reality and what we call mind are two ways of describing the same underlying essence. From the outside, it looks like matter and fields. From the inside, it looks like experience. These perspectives are speculative, and they raise problems of their own, like how small bits of proto-experience would combine into a unified mind. They may not solve the hard problem so much as redistribute it, but they are attempts to include mind in the fabric of reality, rather than treating it as an inexplicable add-on. Entertaining them can bring a quiet, gentle awe. Perhaps the division between world and experience is not final. Perhaps there is a deeper unity we have not yet grasped. The universe looking at itself. Whether or not consciousness is fundamental, we humans undeniably are conscious, and through us, one might say, the universe is looking at itself. This is not a scientific theory, but a poetic truth that resonates deeply. Carl Sagan said, "We are a way for the cosmos to know itself." Every atom in your body was forged in ancient stars. You are made of star stuff, scattered across the galaxy and reassembled here into a being that can look up and ponder those stars. In you, the cosmos has curiosity. In you, it wonders. There's no need to imagine intention or destiny. For billions of years, the universe existed without conscious observers. But here, in this corner, matter has arranged itself into a being that can ask, "What am I, and what is all this?" The neurons firing in your brain are part of the same universe as the sun and moon, and they have become the seat of a viewpoint that can contemplate the sun and moon. It's as if the universe has scattered pieces of itself that, under the right conditions, wake up. Each of us is like a tiny mirror reflecting a corner of the cosmos. When you feel wonder beneath a night sky, that is the universe experiencing wonder through you. This doesn't require believing the universe has a single mind. It's simply the realization that our minds are not separate from the universe. They are born from it, part of it. And that means the story of the universe is not only matter and energy, but also observation, interpretation, and meaning. Meaning that we, the observers, create. What we can say honestly. After traveling through these questions, it's important to return to what we actually know and to name what we don't. Consciousness and the brain. Reliable evidence indicates consciousness is closely tied to brain function. Changes to the brain through injury, drugs, and illness change consciousness. Specific brain areas correlate with specific aspects of experience and cognition. This strongly suggests consciousness is intimately connected to a physical substrate, and most scientists operate under the working assumption that consciousness emerges from complex neural interactions, even if the mechanism of subjective experience remains unknown. There is no empirical evidence that consciousness exists independent of a physical substrate, nor that exotic quantum processes are required for basic brain function. Quantum physics and observers. Quantum theory has been tested to extraordinary precision. Whether a person watches or an automated detector records, the equations work the same. We can run experiments with nobody present, and later checking the results matches quantum predictions, as if observation occurred at the device. This supports the mainstream view that observer can be understood as interaction that causes decoherence or produces a record. There is no experimental proof that human consciousness causes wave functions to collapse. No final theory of consciousness. We do not have a scientific theory that explains why subjective experience exists. We have strong theories for behavior, cognition, and neural processing, but the first-person feeling remains elusive. No proven link between quantum and consciousness. Despite speculations, there is no empirical evidence tying quantum phenomena to consciousness in a causative way. Measurement problem unresolved. There is no consensus on which interpretation of quantum mechanics is correct. For practical work, physicists often set the conceptual dilemma aside and use the theory successfully. What remains unknown? How brain activity becomes experience, whether consciousness is emergent or fundamental, whether quantum mechanics and consciousness are unrelated mysteries or linked by a deeper theory, where the threshold of mind lies, and whether consciousness ignites sharply or fades in a spectrum, and what the ultimate nature of reality is beneath quantum mechanics. Why uncertainty is not failure. Not having the answers yet is an honest reflection of reality. Acknowledging gaps is a strength, not weakness. We don't know has often been the starting point for discovery. Uncertainty keeps us humble, and it keeps wonder alive. The universe is not obligated to match our intuitions. Admitting "I don't know" keeps the mind open. So we hold these questions gently, we stay curious, and we allow ourselves not to have the solution tonight. Closing stillness. We've travelled a long way in our reflections, and now we return to the simple fact we started with. Here you are, conscious in this moment. Feel the quiet of your own mind, the gentle rise and fall of your breath, the weight of your body where you sit or lie, the subtle play of thoughts and feelings passing by. This is that miracle again, awareness, just being. All the mysteries remain. The universe holds on to its secrets. Maybe one day humanity will unravel more of them, or maybe some questions will stay unanswered. Either way, right now, it's okay. The mystery itself is not threatening. It's something we can even cherish. The night is still, and the stars are out there, shining as they have for billions of years. The universe continues on, whether someone is watching or not. Worlds will keep spinning. Particles will continue their quantum dance. Life will go through its cycles. And here, in this small corner of it all, you are aware of just a tiny sliver of existence. This sliver we call our experience. Not knowing the ultimate answers doesn't stop the world from being what it is, and it doesn't stop the present moment from gently unfolding. We can let ourselves simply be, without pressing for conclusions. In a way, we ourselves can collapse the frantic wave of questions into a calm state of acceptance. Acceptance that some things we do not know, and that's all right. Feel the stillness now. The thoughts from this journey may still be swirling a little, but they can settle in their own time. There's no rush. The wonder we feel doesn't need to reach a final verdict. It can linger as open curiosity, as quiet awe. We end not with a firm answer, but with a kind of peace. The peace of not having to have all the answers tonight. The strange fact of your awareness remains. The vastness of the cosmos remains, intertwined in ways we don't fully grasp. And in this moment, you are here, a tiny conscious part of it, breathing, existing, witnessing.